Okay, please let me know if you could see the slide on sample problem number 1, equal size CSTR in series. Can you see already the slide on the sample problem?
Yes, miss.
Now, for this particular sample problem, we'll be now utilizing some of the formulas, equations that were discussed yesterday. And for this sample problem, you will process your feed using two CSTRs. So a problem goes this way. So a 2 storage battery is being used to obtain 80% conversion under the following conditions. So 2-stage battery, meaning it's referring to 2 CSTRs in series. So the degree of conversion is 80%. Now, the volume that needs to be processed on an hourly basis is 75 cubic feet. The initial concentration is 1.5 pound mole per cubic feet. And you're provided with the rate law, which tells you that your reaction is first order with respect to A. So it's 0.2 C sub A for the rate law. Now, working on the set units, pound mole per cubic feet per minute. Now, this particular 2-stage battery has been working, and after several days of operation, the process was stopped, meaning they are not anymore working simultaneously. So it's not anymore a continuous operation for this 2-stage battery. The two reactors are dumped when the average of their concentration is the same as the steady state effluent from the last reactor under normal operating conditions. So the normal operating conditions here that is referred in the problem is that the CSTRs are connected in series and they function continuously. That's the normal operating condition. So in the first statement, it was mentioned here that after several days of operation, the flow is stopped. So meaning they're not anymore connected, and each of the CSTRs in your series is going to process the system that is in it individually after it has already processed it continuously. Okay? Now, you are being asked how soon after flow is stopped can the material be discharged, assuming that this discharge is instantaneous. Now, what does this mean? So the CSTR is operating continuously. They are connected. After several days, they were stopped, and the CSTRs are going to process the system inside them individually. Now, you will stop this particular scenario in which the two CSTRs are processing the system inside them individually when the average of the concentrations of the two systems in the CSTR will be equal to the concentration of the effluent coming from the last CSTR if it is operating on a continuous mode. So the question is, how long after the process was stopped, or how long was the normal operating condition was stopped, will you also discharge the material in the two CSTRs? So the condition that has to be met is that the average of the concentrations inside the two CSTRs after concentration was stopped should be equal to the concentration of the effluent from the last, or the discharge from the last CSTRs if they are processing the feed continuously. So the question is, what is this particular time? Now, do you understand the way I simplify the problem? Because there is this term here, the two reactors are dumped when the average of their concentration is the same as the steady state effluent from the last reactor under normal operating conditions. So you stop the operation of the two reactors when the average of the two concentrations are already equal to the concentration from the last reactor under normal operating conditions. So you are asked of this processing time. Do you fully understand what the problem is asking? Do you need further discussion on what the problem is asking from you and what it is discussing or providing as the given information? Okay, so if there are no questions, you may take a picture of this one. If you're uh, using your cell phones, then you may take a screenshot. That way, when we go to the solution, you can still follow through our discussion. So I will now share the board, the Jamboard, and have this particular problem solved. Okay, just wait, class. Okay, hopefully you can see the Jamboard already. Can you see the Jamboard?
Yes, Miss.
Okay, so we'll write the given information. So the information that will give a picture to anybody who's looking into your solution. Also the same thing with you as to how well you understood the information provided. So you have two CSTRs here. So they are said to be identical CSTRs. So you have one feed here, and then the discharge from the first is being processed in the second, and you have this one as the last. So in here, you have your initial concentration, and you have also here your molar feed rate. But since the problem does not give it, so we will not anymore label it that way. You have here CA1. This is also CA1 here, the concentration inside your first CSTR, and this is your CA2. Now your CaO is given at 1.5 pound mole per cubic feet. And the rate law is equal to 0.2 C sub A. So working on the unit pound mole per cubic feet per minute. And then you are given that your degree of conversion is 80%. So that must be referring to the degree of conversion already on the last tank. So I'll place here X sub AN, which is X sub A2 equal to 0.8. Okay, your volumetric flow rate. So if you have your given information there, the volumetric flow rate is 7.5 cubic feet per hour. Okay, let me check if it's 7.5 or 75. Let me just check. 75, so it should be 75, not 7.5. Okay. Um, is there anything you'd like to add in here? Just give me a few minutes, please. Okay, is there anything that you'd like to add to the information here under the given? Okay, I think we have placed in everything. So you are required for T, or let's say we'll have it represented as T prime. So that's the time after the flow of, or time after the flow of or let's say time after the two CSTRs were disconnected. Because this is also the time for the average of the concentrations of the two CSTRs be equal to the final concentration here on the second CSTR if they are not disconnected. They are equal rather. Okay, so time after the two CSTRs are disconnected. Um, if I will discuss this in Ilonggish para maintindihan nyo, so ang operation din sa duha kasi STR una-una continuous because they are functioning as a battery. So there will be a corresponding may initial may concentration si CSTR1 that would be CA1 and then may concentration man ang discharge ng CSTR2 which is CA2. That is on the fashion that they are working as series of CSTR. Now, pagkauntat sina nila, ginuntat ng ila sina nga operation nga continuous sila, kaging pa-process ang ara na sa sulod nga daas ang CSTR individually by each, but they are not anymore connected. So, ang question is, since the time nga nag-stop sa operation, how long mo sila nga duha, ina nga CSTR nga disconnected, ipa-process further ang ara na nga daan sa sulod nila para ang average ang concentration sa duha ka tangke would be equal to sa concentration sang last CSTR kung nag-ooperate pa siya nga continuous, nga connected pa sila. So that time is T prime. And that's the time that we're going to determine. Okay, so we go to the solution. You may ask questions, interrupt if things are not clear to you. That way, you understand fully the process. So the first thing that we're going to do is, of course, determine the concentration in each of these reactors if they are functioning as this, as a battery of two CSTR. So we will determine CA1 and we will determine CA2. We need these two concentrations here, CA1 and CA2. That way, that will serve this CA1 and CA2 will serve as the initial concentrations of the two CSTRs if they are already disconnected. So that's the reason why you need to determine first CA1 and CA2 in these fashions. And we will do that. So the first thing that we're going to do is we write the equation made available for us. That way we can find the two concentrations. So we'll start with CA2 because we have already the conversion, the overall conversion. So you have this formula Ca2 being equal to CaO times the quantity 1 minus XAN. Now this is comparable to the formula that we have when we're still talking about kinetics, that the final concentration is equal to the initial concentration times the part that hasn't reacted. So the part that hasn't reacted is 1 minus the part that has been converted. So this is the formula. It's just like Ca is equal to CaO 1 minus Xa. In this case, we determine Ca2, the concentration leaving the last reactor based on the initial concentration provided and the overall conversion. And we have all of this. So for CaO, you have 1.5. You have it here. It's 1.5 and the overall conversion is 0.80. So you will have here 1 minus 0.80. So your Ca2 in this sense would be 0.3 pound mole per cubic feet. Now you have Ca2. Next is we determine Ca1 and that's the time that we use the formula CaO, or that's the CO in the formula that was shared to you in the slide, over C, whatever that would be, is equal to the quantity 1 plus K tau raised to N. So this C could be any C, C2, C3, depending on the number of CSTRs that you have in your series. And this N refers to whatever is the number of that particular CSTR that you intend to determine the concentration of. In our case, we have this specifically written as CaO over C sub 2, and we equate it to 1 plus K times the tau raised to, of course, this would be 2. If this is let's say a 3 series CSTR, then this should be C sub 3 and this should be 3. So this is the more generic formula, and this is the specific formula that we're going to use. Okay, now we will substitute the C2 that we have already determined. So we have 1.5 for the CaO rather, and the C2 would be the 0.3. The 0.3 here that we solve. Then we substitute on the right side the things that we are provided already. For the K, based on the rate law, that would be 0.2. And we have the tau, which we do not know. The tau is not given. And there's no way that you can determine it fully because you're only provided with the V sub O. You're not given the individual volumes of the two CSTR. So we'll be determining now the tau based on this formula. So that would be base 2. So your tau in here, the space-time in each of the individual reactors is 6.18 minutes. This refers to the tau 1, also to the tau 2, because we have identical CSTRs in here. It was not mentioned that we have CSTRs of different sizes. So then it's okay that if it's stated as a battery or CSTR in series, then it's okay to assume right away that they are identical. Okay, then we have another formula that allows us to solve for C sub 1. So we can have pattern from this particular formula. We set up a new one. Of course, that way we can determine C sub 1 in here. So we'll have another formula, CaO divided by C sub 1, and you will have 1 plus K tau raised to, let's say here, 1, because this is also 1. So your CaO is still 1.5. I want to determine the Ca1. This is Ca1. And I'll have here 1 plus 0.2 plus the tau that I have here. So this is 6.18. Now it's raised to 1 because we're determining Ca1. From in here, you'll determine already the Ca1, which is 0.6708. So this is pound mole per cubic feet. So now you have determined the Ca2. This is your Ca2. I like to underline that because we'll be needing it. Or just use an arrow. And this is your Ca1. Okay. Now you'll be using these concentrations of the discharges of your first and second reactors when you set up the individual rate equations if these reactors are already processing the system inside them individually. They are already disconnected from each other. So if you're going to write the equation for that, since you have a first order equation, so for n equal to 1, so for the two systems inside CSTR1 and CSTR2, you have dCA dt equal to kCA. So this is your more generic formula. And from in here, you will have, from what we have discussed already in kinetics, you will have C sub A over CaO equal to kT. So this is our more generic formula, which we can simplify further to Ca being equal to CaO e raised to negative kT. So this is for a first order reaction in which you want to determine the concentration after some time inside your reactor for a particular initial concentration. Okay, So for N, for the first reactor, I'd like to write here for N equal to 1, for the first reactor, your C sub A, for that, its final concentration, let's say I will denote it as C prime, that would be equal to the initial concentration for that particular reactor will be the concentration of the discharge from it when the operation was stopped. Okay, when the operation in the two reactors was stopped, this particular concentration of the discharge from the first reactor will be the initial concentration that you're going to use in here. So I'll place here Ca1 e raised to negative. So your K is 0.2 and this is the T prime. The T prime that you'd like to determine. Okay, now your Ca1 is 0.6708. So I will have your C prime is equal to 0.6708 e raised to negative 0.2 T prime. This is for the concentration in the first reactor after T prime. Now for the second reactor, so that would be N equal to 2, you will have the same format as this one, but this time will represent the concentration in it as C double prime after time T prime. And it's going to start with the initial concentration, which is Ca2, because that's the final concentration of your discharge when operation was stopped. So this is E raised to negative zero point 0.2 and this is still T prime. So if I will substitute now the Ca2, that's 0.3, you will have here 0.3 E raised to negative zero point 0.2 T prime. Now, we have determined the concentration C prime and C double prime in your first and second reactors after time T prime. So this is the time that the reaction would still proceed after the connection was stopped, okay, or after the tanks were already disconnected. So if you're going to use the condition that we will stop at time T prime when the average of these two is equal to the concentration of the discharge from tank 2 under normal operating conditions, then that particular formula would be this, using that condition. So your C prime plus your C double prime divided by 2, because we're taking the average, should be equal to the discharge concentration from tank 2 under, or CSTR2 under normal operating condition. So you copy the right side of these two equations. So this is equation 2 already. So we have 0.6708. And we have here 0.3. This is multiplied to E raised to negative 0.2 T prime. And we divide this by, sorry, and we divide this by 2, and the Ca2 will be the Ca2 that we had used a while ago, the same Ca2 that we have determined initially here, which is 0.3. So this is equal to 0.3. So you will have a corresponding time there, the time after the operation of the two tanks was stopped, the time that you need it to operate separately. That way, the average of the two concentrations inside the reactors will be equal to Ca2, which is 0.3. So in here, your T prime is, you can check it, it's 2.4 minutes. So after the connection is stopped, you need to wait for 2.4 minutes so that the average of the concentrations in each of the reactors will be equal to Ca2, which is 0.3. you have any questions here? So that's our flow of the solution. This is our given information. Okay, we determine the concentrations in each of the tanks operating in natural normal operating conditions. Then now we determine the corresponding concentrations at time t prime when they operate separately already. And this is the time. So do you have any questions? So no more question. Okay, so if there's none, and go back to the slide. And we go to this part here. So that's the solution to this problem was already shared to you. And we go to this part. So if we have already MFRs of different sizes, then you just have to set up separate performance equations for each of your CSTRs. So let's say, for example, in this illustration, you want to set up the performance equation just for this CSTR, the first one. So this is for n equal to 1. This is 1, this is 2, and this is 3. So this would be your corresponding performance equation. Notice that this time your concentration, your numerator is not written as CaO XA1 conversion in the first tank, but it's now expressed in terms of concentrations, and that is CaO initial concentration minus the final concentration, because these two are just the same as CaOXA1. Okay, as suggested by Levenspiel, that if you're working on CSTRs in series, it would be best that you use concentrations rather than conversion in your performance equation. Now in here, in your rate, in the rate equation in the denominator, this should be written, since this is the rate at tank 1 or CSTR1, this should be, let's say for example, your reaction is first order. Let's say your R sub A is equal to KCA, then this must be KCA1. Now, if it's a different tank that we're talking about, let's say for example, we talk about tank 2, we're now talking about this tank, and still we want to write its performance equation. That would be V sub 2, the specific volume of this particular CSTR, still divided by the same volumetric flow rate. So if they are to be connected, the amounts that they will process should be the same. Otherwise, one tank will go dry, the other one will go empty. Okay? Somebody is writing on the chat box. Waay siya nag-slideshow. Okay. Wait, class, ha? Is it on slideshow already? Is it on the slide which has the MFRs of different sizes in series? Okay, how come? Oh, yes, miss. Last, please react right away because I have already used up minutes in discussion, and then after 5 minutes pa naghambal, nawala siya, nag-slideshow. So I'll be repeating what I am discussing. Wala siya ga-slideshow. Is it on the slide? Is it on slideshow mode already? Okay.
It will,
What about this? Okay, thank you. Now, as I was stating a while ago, so let's say we'll talk about this as tank 1, CSTR1, this is CSTR2, and this is 3. Then for N equal to 1, or let's say for I equal to 1, I'm referring to this particular CSTR, this will be your performance equation. The volume of this particular tank, because our tank now are not having the same sizes, so they are different already from each other, and we have here the volumetric flow rate. So we just write it a small letter V because whatever is the volumetric flow rate here, that would be the same volumetric flow rate here, same here. Okay? Now, I have said a while ago that notice that the numerator in the performance equation on the right side is not anymore expressed in terms of CAO, specifically XE1, when we talk about tank 1. But it's now expressed in terms of the difference in concentration. So CAO minus CA1. This is based on the suggestion of Levenspiel that whenever you are processing or working on a problem concerning CSTRs in series, whether they are equal in size or not, express your performance equation in terms of concentration, not conversion. Although you may do that as well, but just so that it would be easy for you to substitute values, so you work on concentrations. Okay? Now, you notice here in the denominator of the same performance equation, you have rate uh, referring to the rate in CSTR1. Specifically, let's say, for example, if the rate law for this reaction is KCA, then for this rate in tank 1, you will have it represented as KCA1. Why it has to be specific to be KCA1? So your numerator now is CAO minus CA1 divided by KCA1. Because if we talk about, let's say, for example, tank 2, or that's I2, your performance equation would be volume of the tank divided by volumetric flow rate equal to, so this time you will have to work on concentrations. And the initial concentration that is in your tank 2 would be now CA1, because it's the thing that your tank 2 receives, minus CA2. And the rate law here in the denominator will be the rate in tank 2, and that will be KCA2. So that is why it's specific here for the rate law that it has a subscript of 1. because the rate law for the other tanks will not be equal to the rate law for the first. In terms of form, they are the same. But as to the value, as to the rate, specific rate, they will be different. So this is how you write the performance equation for tank 2. So if it's for tank 3, I write it here. That would be V3 divided by volumetric flow rate. This time, you will have Ca2 minus Ca3. And the rate here, the rate law is the same in form, but the rate would be written differently. So it's different from this one. So it's KCA2 for tank 2, KCA1 for tank 1, and now it's KCA3 for tank 3. Now, this one is just the reciprocal of this, but written specifically in terms of the IET reactor. So that's the one that I'm writing in here. Okay, ginsuli lang siya. So if this is reactor I, so you will have C sub I minus C sub I 1. Okay, suli siya. Negative, negative, because supposed to be, this should be C sub I 1 minus C sub I. Okay, like this one. So that is why this two is interchanged. So this, because of this negative sign in here. If this is positive, then you will have here C sub I1 minus C sub I3, 2 rather. You have any question as to how you write the performance, individual performance equation for MFRs in series and equal in sizes? Okay, none anymore. Sige, I hope everything is clear because oftentimes this is where the error or majority of the students are committed in terms of the rate and also in the numerator, the way they subtract the concentrations in the numerator. The left side is so easy because you only have the volume and the volumetric flow rate to consider. Let me clear this if there aren't any questions, and we'll proceed. Now, there are thoughts to ponder for you in this particular slide, and that would be your assignment. You can check on it, and we can discuss your answer to these questions next week when we see each other on Monday. Okay, when we meet again on Monday. So, if you are to compare the volume for the following two cases, a single reactor achieving the same degree of conversion, let's say you only have one CSTR and the conversion, let's say, is 90%. And then the other case would be you have three CSTRs in series achieving the same degree of conversion, which is 90%. How will be the total volumes of these three reactors compared to just one reactor? You can use the performance equation. That way you can answer this question. And we will discuss the answer to this question next meeting before we proceed with the next sample problem. So let's say you have a single CSTR having a particular degree of conversion. And you have three CSTRs having the same degree of conversion. How will the total volume of these three identical CSTRs compare to just this one CSTR of the same degree of conversion? That's the first question. The second question is, can we model your PFR as a series of n equal volume CSTRs? So can we have the same degree of conversion in your PFR in which the volume is equivalent to n CSTRs equivalent to the PFR. Let's say your PFR has a volume of 50 liters. Then you will use, in this case, example 5 CSTRs at 10 liters each because you have 50 liters of PFR volume. Will this be achieving the same degree of conversion? So that's the next question. So all of these questions actually can be answered using, of course, your performance equations for a single CSTR, for 3 CSTRs in series equal in size, and for your PFR. And we will have the answer to these questions discuss next meeting to give you time to think and do the exercise on your spare time. Okay, since I think I haven't yet given you a problem set on this particular topic. Okay, now we proceed. Now it could be also that uh, you can have CSTRs in series equal in size, CSTRs in series unequal in not equal in sizes. You can have PFRs in series. So we have discussed this. They behave as one PFR with volume equal to the total volume or the sum of the volumes of the individual PFRs. Now this time we go to reactors of different types in series, different sizes, different types in series. So your X sub n here for this particular setup is the most of A reacted up to reactor n. So meaning in here divided by the most of A fed to first reactor. So the most of A that is fed here in the first reactor and the most of A reacted up to the nth reactor. That is your X sub n. Now, if you're going to write the performance equations for each of these, as long as there are no side streams, meaning there's no other additional feed here. So the feed in the PFR is just coming from the discharge of the CSTR. And same thing with this third CSTR or this third reactor having the feed from the discharge of the PFR. So no side stream, so it's only processing the discharge of the previous CSTR. This would be your individual performance equation for each. So for the first CSTR, you have here V sub 1. In your formula, actually, it's V sub 1 over V. And we have here CAO. Then you have XA in this case. Now, we want to represent the performance equations in terms of molar feed rate because you could see that you have already FAO here, FA1 here, and FA2 here. Same thing in here, FA3, the discharge in the third reactor. So originally, if you're going to write it here, for the first tank, your CSTR, that would be V sub 1 divided by V. So I'd like to write the volumetric flow rate here. It would be the same for all. The same volumetric flow rate equal to, so this would be actually CAO minus CA1. And you will have here rate 1. Okay, so that's for your first reactor. Now, I'd like to take out the CAO here. Take out the CAO. That way you can place it in here. That way you can represent this now as smaller feed rate. So how do you get CAO from this one? So you could see in the formula that it is now expressed in terms of conversion. X1 minus XO. So how could that be? So you will have here CAO. If this is represented, this is actually CAO 1 minus XA1. Right? You can place the CAO here. So you will have now B over CAO small b. This one would be now molar feed rate, and you are left with 1 minus XA1 divided by the rate in this first CSTR. This 1 minus XA1 class could be represented as the difference between XA1 here. This XA1 is the same XA1 here minus XAO if there is initial conversion on your feed, or if your feed is initially or partly converted before it's being processed in your first CSTR. So that would be XA1 minus XAO for your 1 minus XA1. So we can write from in here, can write now V over your CAOV is FAO equal to this one. Take note, can be presented as this, XA1 minus XO divided by the rate. Okay, in tank 1, or that would be the case. Now in here, it's in terms of conversion. But if you want to express it in terms of concentration, Levenspiel here is just giving you an option. Then it could be presented in this manner here. Now for the PFR, this is your PFR, you will have V sub 2, this is FAO still, and this time you have dx over the rate here. So actually, originally for this one, you have also CAO dxa, right? If it's PFR, CAO dxa over the rate. This rate, by the way, would be, let's say, KCA2 if we're talking about a first order reaction. So the CA that should appear here will be CA2, okay, in the rate expression, just like if you're processing it as a CSDR, not an NF, yes, not a PFR in this case. So it would be KCA2. The CAO is multiplied together with the V here. That is why you have FO again. So yung papanaog lang na da siya ho. And then your CAOV is again FO. That's for your PFR. For your second CSDR, and that's your third reactor in the series, you have its volume divided by the same molar feed rate. Initial, this is actually FAO. And you have here the difference between the conversions. Conversion here in the third tank minus the conversion here in the second tank, divided by the rate law referring to this particular tank. And that's your KCA3. So you have now a different take on how you will present the performance equations for your reactors in series in terms of conversion. Now, if you're wondering why, if it's suggested that we will express our performance equation for the CSTR in terms of concentration, why now express our performance equations here for the three reactors in terms of conversion, if it is suggested that it would be best to work on concentrations? Now, the answer to that, class, is because you already have the PFR. And the PFR is processed, its performance equation is processed using the unknown function x sub a. So the integral is based on the unknown function x sub a, not in terms of concentration. So it would best that all your performance equations then should be expressed in terms of conversion rather than concentration. But if it's a system that is all CSTR, whether equal in size or not equal in sizes, then it's suggested that you work on concentrations. If it's a mix, better use conversion, primarily because of the performance equation of your PFR, which is in terms of conversion. Okay? You have any questions for this one? Our discussion next meeting will be now using this particular sample problem, which will be now using a CSTR and a PFR, so a combination of the two different reactors. But before we go to that, I have this one in here. This is in the case of showing graphically on what would be the corresponding sizes of your reactors for this type of system. The V1, V2, and V3, the sizes of these three reactors. So you have the formulas in here already summarized for you. Again, the formulas are all based on conversion because your PFR performance equation is in terms of conversion, not concentration. So you have this for the first reactor, you have this for the second reactor, and that's your PFR, and you have this for the third reactor. What actually happened is that you just transferred from in here, you just transferred the molar feed rate here, cross multiplied it on the right side of your performance equation. So you have this one now, You have only x1 here. That's on the premise that mostly class the feed is not partly converted when it's being processed on the first reactor. That's on the premise that your XAO is 0. So that is why you only have x sub 1 here, and you have rate here, rate 1, and you have here rate 3, and this is your more general equation for your PFR. Okay? In terms of the answers to these equations, so this would be the area under this particular rectangle, the area under this rectangle, and this one is the area for the PFR. So you have it curved here because of this one. These two are rectangles because this is just like a box if it's represented in terms of an area. Okay? So next meeting, that would be Monday, we'll be discussing the solution to this. Let me check what we have here next. And this one. Hopefully two sample problems so that this would be left for you to be processed as part of your module requirement. Any questions?